Hello everyone, welcome to Kepler. Today we are going to solve another GFG problem of the day. Today's problem is elements in a range A, B. Now, the problem statement says given an unsorted array and a 2D array queries of size q, where each query is in the form of bracket A, B. For each query, count how many elements in array lie within the range AB, that is, elements satisfying this relation A less than equals to X less than equals to B. Now essentially the question wants to say that we have been given an array of numbers. Now a query of this format where each element represent two integers, one x1 comma x2. Now essentially we need to give the count of element that satisfies the following relation: x1 less than equals to any element y less than equals to x2. So I need to find count of all these uh, element that satisfies this condition. That means count all those y that satisfies this. A naive way to solve this problem can be directly traversing over the array for each query. That is, for every query x1 comma x2, I will traverse the entire array and check whether each element or any element array of I follows this relation. If it does, then I will count, or else I won't. That is, for an example, if I for this query 3 comma 6, I will start traversing the array. First I will get 1. Does 1 falls in this range? No, it won't, so I won't count it. Now coming to 4 is greater than equals to 3 and less than equals to 6. That means 4 will be counted. My count is currently 1. Then 2, no, 2 also doesn't fall in this range. Then coming to 8, sorry, now 2 is done. Now coming to 8 is actually greater than 6, so it also doesn't fall in this range. Now coming to 5 actually falls in the range of 3 comma 6, so I will again count it, so my count will become 2. So for this query 3 comma 6, it will be 2. Now I need to perform this for all this query and store my answers inside a vector and return it finally. Now coming to the complexity of this approach, for each query I am traversing the entire array again and again, so my complexity will be size of the query or size of queries q into number of element in the list n. Now as it is given that size of the query is 10 to the 6 and n is also around 10 to the 5, so my complexity will be around big O of n square. And can we have to optimize this? Because this solution won't be accepted, it will be partially accepted. So coming to optimal approach, now what if, now as I need to find the element within a given range, can I sort it? Because the range is actually sorted, 1 comma 4, 1 is less than 4 and 4 is greater than 1, so it's actually sorted. So what if I sort my array? If I sort my array becomes like this. If I sort my array, then the sorted array will be like this. Sorted array will be 1 2 4 5 8. 1 2 4 5 8. Now for the first query 1 comma 4. Now what should be the approach to optimize it? 1 comma 4 for any given range. Forget 1 4, for any given range x1 and x2. x1 and x2. I need to find all this element here. Now what if I can find the smallest index inside the array that have value greater than equals to x1 and the largest index inside the array that have value less than equals to x2. Now as my list is now sorted, if I can find these two elements, that is a number greater than equals to the my left range and number less than equals to my upper bound, that is if I can get the indexes, then my solution must be this value, the lower, and if it is upper, then my solution must be upper minus lower. For an example here, 1 2 4 5 8. Now the given range is 1 comma 4. What is the smallest number in the array that is greater than 1? Or what is the leftmost index in the array that is greater than 1? That is 1 itself. Here my index is 0. Now what is the largest number in the array that is less than equals to my upper bound? 4. It is 4 itself. Now here the index is 2. Now what essentially need to do is count the number of elements in between 0 and 2. That's nothing but 2 minus 0 plus 1 or 3. In general way I can write it h minus l plus 1. Now coming to another example, 1 2 4 5 8. What if I took the second example, that is 3 6? 3 6. Now what is the largest number in the, what is the element in the array, smallest element in the array that is greater than 3? That is 4. 4 is the smallest element in the array that is greater than 3. And what's its index? Its index is 0 1 2, actually 2. Its index is 2. Now what is the largest element in the array that is lower than the my right side bound, or 6? The largest element in the array that is smaller than 6 is 5, of course. Now, so what's its index? 3. Now I need to count the number of elements between the index 2 and index 3. That is 3 minus 2 plus 1. That is 2. 4 and 5 itself. So my answer here will be 2. Now, I know that this is a solution, but how it optimizes? Now, the main question is, how can I find the number that is greater than the smallest number that is greater than equals to my lower bound, and the largest number that is less than equals to my upper bound. Now here comes the concepts of lower bounds and upper bounds. It is an important concept of binary search, where I can find for any given number, in a sorted array, say ARR, for any given number x, I can actually find the number that is greater than equals to x, or I can actually find the lowest number that is greater than equals to x, this is called the lower bound, and the highest number that is less than equals to x, that is the upper bound. Now I need to calculate those, but actually here I don't want the element itself, I want the index of the element, so I will tweak my approach. Now coming to the pseudocode of lower bound and upper bound, how I can calculate that. For lower bound, function lower bound, I require the nums and the element for which I am calculating the lower bound. Okay, so what are the things I require? First, in the for the classic binary search, I require the low and high. As the numbers are within the range of 10 to the 6, so long is not required here. It will be n minus 1. Here n represents the size of the array. Now while low less than equals to high, I will calculate my mid, or just represent it by m. Now what are the things that I am going to check? If in lower bound I need to calculate the number that is greater than equals to x, smallest number greater than equals to x, right? So if first of all, if my now this number that is here I have taken nums, right? So if nums of m is actually smaller than my x, if nums of m is actually smaller than my x, that means what? I will just move forward, because I don't want the number smaller than x, I want the smallest number that is greater than equals to x. So I will shift my search towards the right hand side. That means low should be m plus 1. Else that means the else means, one second, else means my nums of m is actually greater than equals to x. Now what if my nums is actually greater than equals to x? Greater than equals to x satisfies my condition, but I need the smallest number. So even if it's greater than equals to x, I need to come down and look for the smallest number that is greater than equals to x. So in the else part, I will try searching towards the left. So I will move my high towards m minus 1. That means now in the next iteration I will search in the left part of the array. And also one thing that I need to do is I will save my answer. That is, index should be my current m. Now once these conditions L less than equals to h converges, I will just return my index. Now this should provide me the index of the number greater than equals to x, or smallest number greater than equals to x, I would say. Now coming to the upper bound. Now upper bound, actually the approach does not change that much. It's just some notation changes for the upper bound. For the upper bound, goal is to find largest number in array less than equals to x. For the upper bound, I need to find the largest number in the array that is less than equals to x. So upper, let's name it upper. I need the array, I need x. Now let's go. Again, for binary search, L h should be n minus 1, while L less than equals to h. Calculate the mid. After calculating the mid, now comes I need the largest number less than equals to x. So if array of m is already greater than x, then I actually does not satisfy my condition at all. That means I will, as the number is already greater than x, that means I will move my search towards the left. That means high should be mid minus 1. Else, here else means array of m is actually less than equals to x. Now this partially satisfies my condition, but I need the largest number that satisfies this. So I will move my search towards the right to find the largest number that is less than equals to x. So I will move towards right. That means left should be m plus 1, low should be m plus 1, and also I will store my answer because this partially satisfies my condition. So my index should be m, and I will move. Okay, so after this condition converges, I will return index. So this will provide me these two values, provide me the value. Okay, so this upper and lower function for any given query x1 x2 should provide me the highest value lower bounds and upper bounds, and by performing this operation, upper minus lower plus 1, I can find the count of elements that satisfy the condition of that are within the range of x1 and x2. So now if I code this part up, so it will be like this. First, okay, so let me first sort my array. Okay, now coming to the two functions, that is lower and upper. This function should be calculating the lower bound. Let's name it lower. I require the vector and the value. Initialize the low and high. Now, okay, so I also need to initialize the index. Index can be a default value like -1. It helps when it finds nothing, then I can actually return -1. Okay, so now coming to the main condition of binary search. Okay, calculating the mid. If for the lower, if nums of m less than equals to x, so the first conditions, if array, so in this case it would be array of m less than, I need to find the largest index that is less than equals to x. So if array fm is also already less than x, then I will just move my search toward the right hand side. That means L should be m plus 1. Else, in the else part I will store my answer first. Index should be m, and then move my search toward the left hand side. Now just return index. Upper. Now for the upper part I will just copy this and make the changes over there. First make it this upper. It's all fine. Okay, now coming to the main conditions, that this for the upper, if I need to find the smallest index greater than equals largest index less than equals to x. So if array of m is already greater than x, then I don't want that. So if array of m is already greater than x, then I shift my search toward the left hand side. That means h should be m minus 1. Else I will be storing my answer index equals to m, and shift, as I want the largest index, so I will shift my search toward the right hand side. L should be m plus 1. Okay, so I think the function are written. Now let's handle the queries. Coming to the query part, now for each query, I will search for the lower and upper bound. Sorry, let it be low, that would be better. Lower of, need to pass the array nums, and okay, so I need to find the lower bound of the first index of the query. That means it of 0. I need to find the upper bound up upper bound of the second index of the query. That means the right side, right bound. Now after finding the lower and upper bound, that means I have found these 2 points for any range x1 x2. I have found these 2 points, lower and upper. Now counting the number of elements between them, it's just, I can return up minus low plus 1. It should be working. But now coming to some edge cases. First of all, what if inside of the array, now coming to the edge cases, okay, let's first execute this, then I will come to the edge cases, compile and run. Okay, so I have not given the return type, sorry. My mouse is glitching for some reason. 90 upper and 90 lower. Okay, so sorry. I should not be returning this. I actually need to put for each query I need to put everything inside of an array first, vector first. Let it be answer. Now for each query I need to push it inside of the answer dot push back low minus up plus 1, sorry, up minus low plus 1. Now need to return this. Okay, let's see if it runs or not. Okay, what are the errors? You is there any error? Return. Okay, there is no error. Index. Lower nums was okay. Sorry. I have mistakenly given nums. My array name is array actually. So yeah, it have compiled successfully, and for the initial test case my result is perfect. But let me come to some edge cases that this code will actually fail. First of all, what if in the array in the given array, if for a range x1 and x2, what if my all the element in the array have is actually less than x1? That means my count should be 0. This is one of the edge cases. For all the element in the array is actually less than x1. And what if all the element in the array is actually greater than x2? Then also my count should be 0. Those two cases should be handled explicitly. Sorry, let me handle them first. Now if those cases happen, this code should directly provide -1, because I have initialized my index with -1. If for any case my condition does not satisfy, that means my index value won't change from -1, so my value will be -1 itself. So again my mouse is glitching. Let me refresh this page. Okay, so just need to write this: if my low equals to -1 or up equals to -1, that means all the elements in the array is either less than low or either greater than up. So just push 0 to the array. I will just be pushing 0 inside of the array. Return else. Okay, let's compile and check. Now it should be fine. Let's submit. Yeah, I think it works. Now coming to some C++ STLs that you can directly use, which will save a lot of time in case of any kind of real life interview or any kind of way you will be giving. Rather than writing this entire code of lower and upper, let me comment this out. Yeah, so actually C++ provide two STL functions that are lower bound and upper bound. C++ actually provide two default functions, lower bound and upper bound. Let it be auto low. I will be explaining those first. Let's check the functions. Auto low, lower bound, it takes beginning
first use your
and the number, that is it of 0. This is the first query, the left side bound of the range, and auto high. It's auto because it's actually providing the pointer, so I have just make the data type auto. upper bound is the same thing. And I can just straight away push this inside of my array. Sorry, up would be good, much better. Up minus loop. Now here in this case +1 is not required. I will explain why it's not required. Now if I again compile this, yeah, it's working, and let me submit it. Yeah, again it's worked. So these two are some this upper bound and lower bound are the STL function provided by C++ directly. You can use them to uh, uh, to reduce your time consumption, but I will recommend to write the functions manually. It will help to understand the code better. Now coming to how this lower bound and upper bound works. Actually in C++, the upper and lower bound for any array containing x1, x2, x3 xn, sorted array first of all, because a binary search operation only works on sorted array. The lower bound actually calculates the it's like traditional lower bound. It will provide you the lowest index, or sorry, it will provide you the index of the element that is smallest element that is greater than or equals to your given value x. That is the classic lower bound. For any given element x, if it will provide the index of the element just greater than or equals to x. And in case of upper bound, it's not the normal upper bound that we have just calculated. In case of upper bound, what it does is that for any given element x inside of the array, it will find the smallest element just greater than x. Previously we were finding the largest element less than or equals to x, right? So in this case it will find the element just greater than x. So for an example, let me again go to the array 1 2 4 5 8. 1 2 4 5 8. Now for the query 1 4, the lower bound will be normal. It will provide 0 because lower bound of 1 is 1 itself. But the upper bound, previously it was providing 4, that is index of 2. But the STL function provided by C++ will provide the open open interval. It actually it's not close interval, it is the open interval. It provides 5 as the answer, thus the element just greater than 4. So in the case of if you are using STLs, you do not require to actually add 1 because it's already providing +1 value in the answer itself. So that's the reason if you are using the C++ STL function of lower bound or upper bound, the answer should be up minus low, not up minus low +1, because the upper bound is not as traditional upper bound. Okay, so that's it. You can use either the normal, you can write the lower upper by yourself, or the C++ STL function lower bound or upper bound. It's on you. Now coming to the complexity of this, as binary search, the complexity should be log n. Search complexity over the array should be log n, and we are performing this for all the query inside of the array, that is q into log n. So as q and n are very close, so it should be around n log n complexity. Thank you very much. We will again come up with a new video.